Quadratic and absolute value transformations. All right, you're able to tell if an equation is quadratic by if its degree is 2. Recall that the degree of a function is just whatever the highest exponent is. You can tell if an equation is an absolute value by if it has the absolute value bars. Remember, those are just 2 vertical bars. All graphs of quadratics are shaped like a U. They're called parabolas. And graphs of absolute values are shaped like a V. Later on, you'll be asked to identify equations and graphs as absolute value or quadratic, and these are the criteria that you're looking for. Okay, what I want you to do here is diagram this equation and tell me what each of these things does. So the negative out front, the A, the H, and the K, just like we went over in the last video. So pause your video, try to do that from memory, and come back and see what I have. How'd you do? I hope you at least got most of these. Couple things I want to remind you. Remember that the H is a little tricky. A plus is left, a minus is right. And with the stretch and compress, we've got, specific values that tell you if it's going to be a stretch or compress. One other thing I want to note is I always want you to think of this negative and this A as 2 separate things. So don't ever see a negative number out there and just think, oh, it must be a compress because it's negative. No, no, no. Negative means reflection, and then whatever the A value is determines whether it's a stretch or a compress. Okay, this problem says describe the transformation from solid to dashed. So we're just going to say how the graph moved. First of all, I want to point out that the graphs in number 1 are absolute value graphs. I know that because they are shaped like V's. In order to tell how the graph transformed, I'm going to look at these little red dots right here. This is called the vertex. I just want to see how it's moved. So I'm going to count, let's see, it went over 3 and up 7. Since it went over to the right, that would be right 3. I know that it didn't reflect because it's not facing down now. A reflection would have ended up looking like this. And there isn't a stretch or a compress because if you look at the sides, they haven't been stretched or compressed vertically at all. Number 2, we're going to do the same thing. This graph, however, is a parabola. It's a quadratic. I know that because they are both U-shaped. All right, first of all, looking at the vertex, those 2 red dots, let's see if it moved, down 3 and left 1. I also notice that this graph has been reflected. There hasn't been a stretch or compress because if I look closely at it, from the vertex, I only go over 1, up 1 on both sides. So see, we just go over 1, up 1 for each of these, so there hasn't been any sort of a stretch or a compress. Describe the transformation from the parent functions. So now we're looking at the equations here. In this first problem, I notice that I have 2 things going on. I have a negative out front, and I have a plus 5. If those weren't there, I would just have my parent function of x squared. So the negative tells me that my graph reflected, and the plus 5 is where the h would be, and so that's going to be a left 5. Now remember, this is the part that's a little backwards. You would think a plus 5 means right, but it's always switched, so this is left 5. I also meant to mention on problem 3 that that is a quadratic equation, and we know that because it has a degree of 2, the squared up in the top right. Problem number 4. While we're at it, we may as well talk about that is an absolute value equation, and I know that because of the absolute value bars around the x. Okay, again, we've got 2 things going on here. We have this 1/3 out front and this plus 7. The 1/3 is where our a value would go, so that's going to be a stretch or compress. Since it's less than 1, it's between 0 and 1, that's going to be a compress. The 7, since it's not inside the absolute value, it's outside, is going to be our k value, which means that is an up 7. That diagram that we just did is going to be great for whenever you're answering these kinds of problems to reference and see if your 7 or your 5 or your 1/3 is in the spot of the A, H, or K. Eventually, I would like you to have that diagram completely memorized. That'll make your quizzes and tests super easy. Problem 5. Describe the transformation from function f to function g. So now we're not doing a transformation from the parent, but we're doing it from one function to another. So let's look at these two equations and see what's different. The first thing I notice is our a value. Function f didn't have a number for a. It didn't have a stretch or compress, but now we have a 2. So that means that one of the transformations that happened was a stretch of 2. It's a stretch because 2 is bigger than 1. The next difference that I see is our h value went from a +1 to a +4. This means that we added 3 on, so if we do a +3, that means that it's going left 3. Notice that there wasn't a k value for either of the functions, so my functions didn't move up or down. Also, there's not a negative out front for either, so there were no reflections going on. Problems 6 and 7 ask us to write an equation for the function by identifying transformations. The first thing I'm going to do to help me out is to draw my x and y axis better on here so I can see where the origin is. We need to look at how the vertex, remember that's this point up here, has moved from the origin. So let's count that out. It looks like we've moved up 2 and left 4. So this will be our k value and our h value. Next thing to notice is that my graph is now facing down. My parent function was originally facing up. Remember how it faces up like this? So we know that we've had a reflection go on. Now, the way that we tell if there has been a stretch or compressor is we have to look really, really close and see how we moved from, how to get from the vertex to the next point. Let's see, we went over and over and we hit the graph. Same thing on the other side. So since we just went one box, there's not been a stretch or compress. Now that we've checked each transformation, we are ready to write our equation. So I like to start by writing down our form with a's, h, and k in there. And then we can go in and we can plug our 2 and our 4 and our negative for our reflection in. So start with our negative because we had a reflection. We don't have a value for a because there wasn't a stretch or a compress. Our h is going to be a +4 because it was left. And the k is up 2, so it's a +2. Big thing to remember, don't forget to put this squared on your answer, or else it wouldn't be a quadratic anymore.
Now let's look at number 7. So if you look at this graph, you'll recognize it as an absolute value. Think about the parent function. Remember that its vertex is at the origin, 0, 0. So think about this graph in red and how it's been transformed. So from 0, 0, the new vertex here that we can see has been moved over 2. It has been shifted 2 to the right. Now let's see how far it has been shifted up. 1, 2, 3. So it has gone 3 up. So if you look, this graph is opening upwards, so we do not have a reflection. Let's check and see if it has been stretched or compressed. So we just go over 1 and up 1 on both sides, so that means we do not have a stretch. So let's write the general form of an absolute value. So y equals a times x minus h plus k. If we're going to shift 2 to the right, that means that we need to have an h value where we are subtracting 2. And if we're going to move 3 up, we need to have a k value where we are adding 3. So now let's write the equation. We'll put it all together. So y will equal, our a value will just be 1, x minus 2, absolute value of that, plus 3.